Okay, let's get started. So I'd like to introduce myself. I'm David. If you have a problem, please come tell me about it. Even though I don't want to take care of it, I will. So I'm going to be talking about analytic bootstrap methods, which by now is a lot of material, especially with the developments in the past year or so. So I'm going to start with, by now, a relatively old version of the analytic bootstrap, which is the Lightcone bootstrap, which is useful for getting some results that Dolly Mill mentioned in his very nice introductory lectures, and for building some physical intuition. But then we're going to switch gears and start building some mathematical machinery with the hopes of introducing Karen Ho's Lorentzian inversion formula, which will give us a new understanding of some of the results coming out of the Lightcone bootstrap. And then we'll see how far we get in that direction. Okay, so we'll start with the Lightcone bootstrap. So as usual, our starting point is the conformal block expansion of a 4-point correlation function. And for simplicity, I'll study a 4-point function of identical scalars. This has an expansion as a sum over operators O in the phi OPE, some squared OPE coefficients, times conformal blocks. And these conformal blocks are fixed completely fixed by conformal symmetry. So for example, a lot of the position dependence is just given by these standard dimensionful factors. And after factoring those out, we're left with a function purely of conformal cross ratios. And in the case of identical scalars, this function of cross ratios doesn't depend on the dimension of the external operator phi. These cross ratios were already defined in Dolly Mill's lecture, but in every bootstrap lecture, you have to write these equations. So the cross ratios are defined by ZZ bar is equal to x12 squared, x34 squared over x13 squared, x24 squared, and 1 minus z bar is the same thing with 1 and 3 swapped. And demanding that this function be permutation invariant, we get an interesting equation relating the dimensions and spins and OP coefficients to each other, and that's the statement of crossing symmetry. So the crossing symmetry equation says that a sum over O of f phi O squared g delta j of ZZ bar, and I'll call this the S-channel expansion, is equal to a sum over conformal blocks in the T-channel. And this prefactor comes from the dimensionful factors up there. We have this factor of 1 minus z bar. This is all to the delta phi, and then times a sum over conformal blocks in the T-channel. And I'll use primes to indicate objects appearing in the T-channel and unprimed things to indicate objects appearing in the S-channel. And that will be useful for later when we're going to have a bunch of different dimensions flying around, some of them from the T-channel, some of them from the S-channel. And this will be helpful for keeping track of them. So in the T-channel, we have conformal blocks with z and z bar replaced with 1 minus z and 1 minus z bar. Okay, so the Lightcone bootstrap starts by studying this equation in a Lorentzian regime. So in Euclidean signature, z and z bar are complex conjugates of each other. But in Lorentzian signature, as Dolly Mill reviewed, that's no longer true. They're independent real variables. So by using conformal transformations, we can put the 4 operators in a plane, and we're going to consider the following configuration. So x1 is at 0, x3 is at 1, and I'll use Lightcone coordinates here. So 1, 1 in Lightcone coordinates. x2 will be at z, z bar, and those look like this. Z goes this way, z bar goes this way. And x4 is going to be at infinity. Okay, so the Lightcone Bootstrap is all about what happens when you approach a part of this square that is not near any particular OPE channel. So this is if x2 is near this point, that's the S channel. If x2 is near this point, that's the T channel. And we understand very well what the physics is there. The Lightcone Bootstrap is about approaching this point in a particular way. So this point is z equals 0, z bar equals 1. So we're actually going to study a very particular limit in this configuration. We're going to study the limit that 1 minus z bar is much, much less than everything else, in particular much less than z, and z is much less than 1. So in this limit, the first thing that's happening is this point is approaching this line, and then from this line, it's approaching the corner. And because this point is extremely close to this, so let me actually, I'll draw a picture indicating what's happening. Because x2 is very close to this line, it senses a singularity, the singularity from being nearly light-like with x3. Now, the singularity when x2 and x3 become nearly light-like from each other is not obviously visible in the expansion around the S channel. And that's the whole point of the Lightcone Bootstrap, to understand how that singularity comes about. So an important fact for us will be that the conformal blocks simplify in the so-called Lightcone limit. And this will let us write a simpler version of the crossing equation that's a little easier to analyze. So the statement is that if you take a conformal block and you look at the leading term in very small z, then the leading term takes the form z to the delta minus j over 2, and I'll sometimes call delta minus j the twist, times a certain special function of z bar that I'm sure many of you are familiar with. This is an SL2, an SL2R conformal block. And specifically, it's given by a power times a hypergeometric function. So deriving this formula, so this is plus higher order in z. So specifically, powers like that and higher. Deriving this formula is one of the exercises on your problem sheet for this afternoon. And I'm sure many of you have seen it before. Are there any questions? Okay. All right. So yeah, I should mention sometimes I'm going to use some notation borrowed from 2 dimensions, where occasionally I'll write h is delta minus j over 2 and h bar is delta plus j over 2. This doesn't mean we're in 2 dimensions. This is just sometimes useful for uncluttering the formulas. Okay, so so we have 2 different limits going on here that we're interested in, and each of them, so specifically small 1 minus z bar and small z, and each of them can be used to simplify one side of the crossing equation or the other. So let's do that. So we're going to use the Lightcone limit of the blocks to write the crossing equation in the following form. So on the left-hand side, we'll use the small z behavior of the blocks. And on the right-hand side, we'll use the small 1 minus z bar behavior. Now, because I'm taking this limit where z bar goes to 1 and z goes to 0, this factor simplifies a little bit. And the other thing I'm going to do on the right-hand side is pull out the leading term, which is the contribution of the unit operator. So the sum on the right-hand side will be over O prime not equal to the unit operator of these simplified Lightcone conformal blocks. And the thing I said earlier about a singularity as x2 becomes light from x3 is visible in the contribution of the unit operator. So the unit operator gives that leading singularity. We have 1 in parentheses, and the singularity is this prefactor out here, 1 over 1 minus z bar to the delta phi. And in this limit, that is getting extremely large. It's the biggest thing on the right-hand side. OK, so let's focus on the contribution of that term. So we're going to look at this and try to understand how it's reproduced on the left-hand side. And as I said before, the way that it's reproduced on the left-hand side is not completely obvious. It takes a little bit of work to see. And the reason is that if you look at a single term on the left-hand side, so specifically we're going to look at this SL2 block that appears here. So remember, for now I'm focusing on the singularity as z bar goes to 1. Okay, so I'm going to look at the z bar dependence of the things on the left-hand side. So if we look at this SL2 block, then it has an expansion in small z bar that looks like the following. So the leading term is a log of 1 minus z bar, and then plus some constant, and then plus order power times logs. And this formula just comes from the standard expression for expanding the hypergeometric function around z equals 1. OK, so the puzzle is that on the right-hand side, we have a power law singularity that we understand very well. It's coming from the contribution of the unit operator in the 2,3 OPE. On the left-hand side, we seemingly don't have any power law singularities. We have only log singularities in each term. So the only way that this can possibly be consistent is if the sum over operators here does not commute with the small 1 minus z bar expansion that we did here. And we'll see an example of that in a second. So in other words, so the sum over operators does not commute with the 1 minus z bar expansion. This is only possible if the sum includes an infinite number of operators. So we need an infinite number of operators in the S channel. OK, so if we have an infinite number of operators, if we have an infinite sum, it's possible for the sum to not commute with the expansion. If it were a finite sum, of course, it would commute with the expansion. So we need an infinite number of operators, but we know something else about these operators. We concluded that there needed to be an infinite number by looking at the z bar behavior of the unit operator contribution, the fact that it's singular. But now we can look at the z behavior of the unit operator contribution. And that looks like z to the delta phi. So that means that these infinite operators that are producing the 1 minus z bar singularity must also produce this z to the delta phi, which means they have to have, so they need to accumulate in twist. Specifically, twist, which is delta minus j, has to approach 2 delta phi. Only if you have an infinite number of operators with twist arbitrarily close to 2 delta phi can you reproduce this term. Questions? Yes?
Maybe a null question. In the relative size of 1 minus z bar and z, 1 minus z bar is smaller.
Correct.
So shouldn't we be just keeping the leading term in 1 minus z bar and having some exact function of z instead of the other way around? Because that's the limit that's taken first.
I see. Yeah, so for the limit that we're concerned with, that gives the same expression. We're eventually going to take small z, and taking small z is, you're talking about the right-hand side or the left-hand side?
Just this.
The left-hand side.
Expansion for the
Yeah. So we're eventually going to take small z, and small z gives this expression for a pretty wide range of z bars, in particular z bars that are very close to 1. I think this expression might actually break down for a z bar like ridiculously close to 1, and there's room there to do more careful analysis about the rate of these limits. But for now, you're going to have to trust me that this is valid in the regime we're interested in. That is a good question, though. Okay. Other questions? Okay. All right. So just by looking at this term, we've concluded that there are an infinite number of operators in the S channel whose twists accumulate at 2 delta phi. And these are so-called double twist operators. So we denote them by the following expression, the following notation. And you can think of them very schematically as being something like phi and then a bunch of derivatives sandwiched between them. Now, this expression doesn't really make sense in a non-perturbative, in a non-perturbative CFT, so I had to put quotes around it. But the claim is that something like this does make sense in the large spin limit. And for those of you who like to think holographically, these double twist operators are like two particles in ADS that are orbiting around each other at extremely large radius. It's such a large radius that they barely interact with each other, and therefore their dimensions are essentially just given by the sum of the dimensions of the two constituent pieces plus an angular momentum term. Okay, and similarly, one can argue that there exist other double twist families labeled by n, and these are schematically phi with some derivatives and then some boxes. Okay, so let's maybe these arguments here were a little bit fast, so let's try to understand in a bit more detail how these double twist operators can reproduce the T-channel singularity. So here's a nice toy model for what's going on. So let's consider the sum. So this is a toy example. Let's consider the sum z bar to the n from n equals 0 to infinity. Now, of course, we know the answer. This is 1 over 1 minus z bar. But if we look at this very naively, it seems to present the same kind of puzzle that we have here. So the puzzle is, well, what if we take a term on the left-hand side? So on the right-hand side, we have a singularity at z bar equals 1. What if we take a term on the left-hand side and expand it near z bar equals 1? What do we get? Okay, so this is equal to 1 minus z bar to the n, which is equal to 1 minus n times 1 minus z bar plus ... higher order in 1 minus z bar. Okay, so now it seems like we have a problem. The problem is that this on the right-hand side is singular, but every term on the left-hand side is regular. And in fact, if we tried to go further than this and actually compute the leading term on the left-hand side using this expansion, we would get the sum from n equals 0 to infinity of 1, which is obviously bogus. Okay, so the problem here, again, is that the expansion in small 1 minus z bar doesn't commute with the sum. And of course, here we can just exactly do the sum, but let's imagine that we couldn't exactly do the sum and try to understand the singularity a little better. So the reason that this didn't work is that the sum is dominated by n of order 1 over 1 minus z bar. So in the limit that z bar goes to 1, the sum is dominated by terms that are farther and farther out at higher and higher n. And here you can see that there's definitely a problem with this expansion if n is large at the same time that 1 minus z bar is small. So we need to use a different expansion. So what we should do instead is find an expansion that is valid for n large with n times 1 minus z bar fixed. That expansion will capture the behavior of the terms on the left-hand side in the regime where the sum is dominated, and will let us actually compute what's going on. Okay, so let's find that expansion. Yes, thank you. I did not say that, but I should have said it. So that's absolutely important. So the conformal blocks are invariant under swapping z and z bar. So here I wrote the statement for small z, so for the first argument of the conformal block being small, but an exactly analogous statement holds for small z bar. And I used that on the right-hand side. Thank you for pointing that out. Any other questions or comments? Let me keep going, and maybe it'll become clear in a second. Okay. I think that'll become clearer when I write the next formula. So, okay. So the idea is that we need to use a different kind of approximation for z bar to the n. And so what we should do is write it as e to the n log z bar, which is approximately equal to e to the minus n times 1 minus z bar. This times plus small corrections in this limit. So what this basically does is it resums all these problematic terms that were order 1 in this expression. And so now we can estimate what happens. We can take the sum over n and approximate it as an integral. And this is a function, we're sticking a function in the integral that agrees with the thing we're interested in the regime that's important. And so now we can do the integral, and we get 1 over 1 minus z bar. And the fact that we got the exact answer is a coincidence. That's because everything here is so simple that, yeah. So good. So this reproduces the correct singularity and explains sort of the physics of how the singularity comes about. And the thing happening with SL2 blocks is precisely the same. So maybe I should pause and say, so someone had a question about what it meant that the integral was dominated. Okay, good. All right. Okay, so good. So there's the same story with the sum over SL2 blocks. This expansion is bad in the same way that this expansion is bad. We need to use a different expansion that's valid in the regime where the sum is dominated. And the sum turns out to be dominated by h bar going like 1 over square root of 1 minus z bar. And in this regime, there's a different approximation for the SL2 blocks. So these prefactors won't be that important for us. The important thing is there's a function of the parameter that's being held fixed in the limit we're interested in. So the parameter that's being held fixed is h bar times square root of 1 minus z bar. And this function captures the entire shape of the SL2 block in that region. So this is valid for very large h bar. And with this quantity held fixed. And this is a Bessel function. I guess it's Bessel K in Mathematica. I don't know if it's a modified Bessel function of the first or second kind. I don't know, but it's Bessel K in Mathematica. Okay. So good. So now this is what the blocks look like in the relevant limit. And I'll just tell you the answer for now. You can get this sort of by reverse engineering, or you can get it later using techniques we'll develop later, fancier techniques. But I just want to show you how it works. So the idea is that the OP coefficients behave in a particular way in this limit. So they grow like some power, some power of h bar. And so the idea is that putting these two things together, you can approximate the sum over these. So, by the way, this expression here is for OP coefficients of double twist operators. And I'll explain what that means a little more in a second. So using these expressions, you can approximate the sum over double twist operators as an integral. So now it's an integral. So what's going on here? So h bar in my definition was delta plus j over 2, and this is 2. This is, let's see, this is twist plus 2j over 2, and the twist for double twist operators is approximately equal to 2 delta phi. So this is approximately equal to delta phi plus j. So you should think of h bar as just j. Okay? So we're doing some sum over j. We're going to approximate it as an integral over j. And the 1/2 is because only even spin operators appear in the OPE of identical scalars. Okay, so we have the 1/2. And then we multiply these OP coefficients times our approximation for the conformal block. And I'll leave it to you as an exercise to plug this into Mathematica. And this reproduces the thing we wanted. Good. So you can argue that a certain correctly defined density of OPE coefficients has to behave in this way, at large h bar. And there are various techniques for arguing that, and I think my favorite is the one we'll get to at the end of this series of lectures. Yeah, if you know if you know the fact that these coefficients are positive, then there are some powerful theorems that will let you deduce that an appropriately defined density of coefficients has to behave in this way. Yes?
Is there any way of systematically knowing what the correct scaling is, like which part of the sum dominates in order to reproduce singularity?
Yeah, that's an excellent question. So there is a conformal frame that sort of makes this large spin limit into a kind of semi-classical picture. And actually, the right way to think about it would be in ADS, if you like. If you have two particles orbiting around each other at very large radius, you have to figure out what the effective cross ratio is that creates that state, and figure out what the effective spin is of that state, what the relationship is between them, and it will give you this relationship.
Physical arguments,
Pardon?
So physical arguments, it's not some mathematical statement that will tell me.
Good. So the mathematical theorems I was referring to, these Tauberian theorems, do give you this on the nose, and it follows from this that this is the correct regime. There are also physical arguments, which is what I mentioned. Oh yeah? Okay. Okay. All right. So my favorite method would be the inversion formula, which hopefully we'll have time to get to. Okay. Good. Okay. So let's go a little bit further. So this was all about matching the contribution of the unit operator. But we could ask about other contributions from additional operators in the T-channel. And let me see. I think I erased that already. So let's write what those are. So let's look at another T-channel contribution. So coming from another block besides the unit operator. So the unit operator gave us this z over 1 minus z bar to the delta phi. And now we're going to look at a subleading contribution from another operator in the T-channel OPE. So it has some OPE coefficient and its associated conformal block. Okay, and this is so far just using small 1 minus z bar. The next thing we're going to do is approximate this at small z. So at small z, this becomes approximately equal to the OP coefficient squared times a power of 1 minus z bar times this expansion of the hypergeometric function that I wrote earlier, which I think has escaped from the board, but I'll write it again. So the relevant term is this logarithm term, whose coefficient is a bunch of gamma functions. So previously for the unit operator, we argued that we needed an infinite set of operators with twists accumulating at 2 delta phi in order to reproduce the z to the delta phi. So now we have a different type of z behavior. We have z to the delta phi times log z. And the contribution to the logarithm will come from some kind of density of anomalous dimensions of that infinite set of double twist operators. So the idea is that we'll assume that these double twist operators have some anomalous dimension. So their dimensions are equal to 2 delta phi plus j. That's the thing we needed to reproduce the unit operator, plus some gamma of j. And let's suppose that the OP coefficients times anomalous dimensions behave asymptotically like a certain power of h bar. So I'll just write out all the coefficients. These coefficients are designed so that we reproduce the right thing in the T channel. Okay, so if you had this density of OP coefficients, then a similar calculation to the one that we did to understand the unit operator singularity will give us this z to the delta phi log z term. So now we can take this density of OP coefficients times anomalous dimensions and divide by this density of OP coefficients and get some expression for an anomalous dimension. So in particular, this operator in the T channel contributes to the anomalous dimension of double twist operators as follows. I'll write it like this, 1 over j to the tau prime. Okay, so the key point is this. So here I'm writing again that h bar is approximately the same thing as j in the large j limit. So we get a contribution to anomalous dimensions that goes like 1 over j to the tau prime, where tau prime is the twist of some operator in the T channel. And the leading contribution to the anomalous dimensions at large j will come from the lowest twist operator in the T channel, which depends on the theory. But you might imagine, for example, that that lowest twist operator is the stress tensor, and then you would get some contribution to anomalous dimensions that goes like 1 over j to the d minus 2, the twist of the stress tensor. So that would be if O prime is T mu nu. Okay, so there are a few comments I want to make about this analysis. So the first comment is that this type of reasoning, at least as far as I can see, can only really tell you about some kind of asymptotic densities of states. It can't really tell you about anything that's happening at any finite value of spin. So for example, it can't tell you that there has to be an operator at every even spin. It could be that the millionth operator is missing and the 10 billionth operator is missing or something like that. So that's one comment about it. Another comment is that you can try to compute subleading corrections using these types of arguments, and it's possible. So you can compute an entire tower of subleading corrections in 1 over j with a fair amount of work, but this is something that was understood over the last few years. One of the nice things about the inversion formula that we'll get to later is that it gives an extremely simple way to compute all of these subleading corrections. And then another comment, a final comment I want to make about this formula has to do with all these crazy gamma function factors that I've been writing. this thing is very interesting. In particular, if tau prime is equal to 2 delta phi, then for some reason the contribution of that operator to anomalous dimension, the contribution of that operator in the T channel to anomalous dimensions in the S channel vanishes, because we have this 1 over gamma of 0 squared. And this is consistent with the existence of mean field theory. So, spoiler, it's okay, mean field theory exists, which is good. Mean field theory is a theory where the only operator dimensions that are present are the double twist operator dimensions exactly, 2 delta phi plus 2n plus j. This theory has no anomalous dimensions, so it has to be that if you compute the contribution of an operator in one channel to anomalous dimensions in the other channel, you'd better get 0 in this theory, and indeed you do get 0 in this theory. But this analysis shows that there's something interesting happening at the double twist locations in a general theory. There's some kind of suppression of their contribution to anomalous dimensions in the S channel, and we'll see a little later that this suppression is, there's a deep reason for this suppression that the inversion formula makes clear. Any questions? Yes? If there are multiple operators with the same spin. So yeah, the claim is that there have to exist certain infinite families of operators, but there could be other operators. In fact, there definitely are other operators whose contributions are subleading in the limit that we're looking at. So it doesn't tell you anything about those. Did that answer your question? Okay. There was another question here? Yes.
So in the Driven functions which you wrote there, there is an exponentially suppressing factor 2 to the minus j. So they're all exponentially small.
Yes.
Is there any physical explanation of this?
So no, that's a convention. So the only convention independent thing is the product of the 3-point coefficient squared times the conformal blocks. And this is really because the conformal blocks that we use conventionally, these nice 2f1 hypergeometric functions, don't actually have the greatest normalization for doing this kind of analysis. So the two to the factors are kind of a fake. Yeah, they're not important. In fact,
like there's no, for instance, any ADS that's something.
No, I don't think so. It's not. This isn't a convention-independent statement. Other questions? Okay, good. So we did this kind of brute force analysis of the crossing equation, and we found that there have to be these infinite families of operators, and we learned something about the behavior of these operators at very large spin. So the next thing we're going to do is switch gears a little bit and start building up some mathematical machinery. This machinery will help us understand a different way of deriving these results, namely the Lorentzian inversion formula, and hopefully we'll also get to the point of proving the Lorentzian inversion formula in these lectures, but we'll see how far we go. Okay, so the machinery that we need is called harmonic analysis, and so we're going to do a crash course in harmonic analysis. Okay, so harmonic analysis is a generalization of Fourier analysis to non-abelian groups. Okay, so we're going to be interested in some group G. So let's say a possibly non-abelian group G. We'll assume that this G has a Haar measure, which I'll just denote as dg. So this is a way of integrating over the group. It's a group invariant measure. It's a measure that's invariant under the group action. We'll also be interested in the space of unitary irreducible representations of the group that I'll call G hat. So this is the space of unitary irreps. And I'll call an irrep, I'll denote an irrep by pi. And I'm going to abuse notation and use pi both for the irrep and also for the representation map. That is the thing that takes a group element to a linear transformation on the associated vector space. In other words, a matrix, a thing that takes a group element to a matrix. Okay. So the starting point for harmonic analysis is a Plancherel formula. Which is an expression for a delta function on the group as an integral over the space of irreducible representations. And things are going to look a little abstract for a few lines, and then we'll start doing some examples, and hopefully they'll become a bit more familiar. So this is a Dirac delta distribution, and E is the unit element, the identity element in G. So,
sorry, do you want like something like 1 over the dimension of B?
No.
Oh, okay.
Good. So, okay, E is the identity element. So the meaning of this is that the integral of some function of G times this distribution integrated with the Haar measure is just equal to that function evaluated at the identity. And we're going to become very good friends with lots of functions on groups. Okay, so that's the left-hand side. The right-hand side is, this is the so-called Plancherel measure. And it's a measure on the space of unitary irreducible representations. It tells you, it instructs you how precisely to sum over representations pi. And then here, this means the trace of the image of the representation map for G. Bigger. Okay. Is the formula okay? Is this bad?
Just formulas are fine.
Okay. Everything bigger. Not everything bigger, just the word. Okay. Okay, good. Okay. And the Plancherel measure can be kind of complicated and interesting. So one of the interesting things about the Plancherel measure is some representations don't, the Plancherel measure sometimes doesn't have support on certain representations. So there are certain unitary irreducible representations that just don't appear in this integral. And then other representations are weighted in some interesting way. Okay. Good. Yes? They're independent objects. They're measures on different spaces. Yeah. dg is a measure on the group. d pi is a measure on the space of unitary irreducible representations. Yes?
Do these representations always finite dimensional, so you can find a trace?
No, they're not necessarily finite dimensional. They're not necessarily finite dimensional. And this integral d pi will sometimes mean a sum and sometimes mean an integral and sometimes mean a sum of integrals It'll mean lots of different things.
The trace is still guaranteed to be defined or like the dimensional representation?
Good. So the representations appearing in the Plancherel measure will be such that this trace is well defined. So I think the best way to show it is through examples. Okay. I mean, probably someone else could give a great answer to that question, more abstract answer to that question. But I'm just going to show you a bunch of examples. Other questions? Okay. Good. So this is just an expression for this particular Dirac delta distribution, but this equation contains a tremendous amount of information. So in particular, you can use it to write an expression for an arbitrary function on the group by just integrating against the appropriate delta distribution. Okay, so that works as follows. So first of all, let's suppose we have a delta function centered at some g naught. Then we can write this as a delta function centered at E of g times g naught inverse. So now we can plug this into the Plancherel formula, and it's some kind of integral over irreducible representations of a trace. And now we use the fact that pi is a representation map. So pi of a product in the group is equal to a product of pi's. And so now we can integrate against a function to get an expression for f of g. So let's say we have some function on the group f of g. We integrate the delta distribution against that. Actually, I think maybe I want to do it the other way around. It's symmetric, so it doesn't really matter. Good. And so what do we get? We get that f of g is an integral d pi trace of pi of g times f hat of pi, where f hat of pi is defined as this integral. And another way to think about this is to write the trace in terms of a sum over matrix elements. So let's suppose that we have some basis, some basis for the associated vector space. Then we can rewrite the trace in terms of a sum over these basis elements. And so, okay, so the key thing that you should see here is these are matrix elements of the group in certain irreducible representations. The claim is that any function on the group can be written as a linear combination of matrix elements in certain special representations, namely those representations that appear in this integral over pi. So the representations appearing in the Plancherel formula have this very special role, that they provide a complete basis for any function on the group, any sufficiently nice function on the group. And these coefficients, I'll call them Fourier coefficients or partial waves, and they're just some coefficients for now. And they tell you what the coefficients are in this expansion in matrix elements. Okay, so this is some type of Fourier transform. And I'll make that extremely clear in a moment. Okay? So everyone deep breath. Okay, we're going to take off our mathematicians' hats now. We're going to become physicists again. We're going to start looking at some examples. Okay. Okay, so first example. Yes. Correct. The trace is in the associated representation.
So that A is actually a dependent on phi.
Correct. The A's and B's depend on the representation. Yeah, you can't swap the sum over A and B with the integral over pi. Other questions?
Are you going to tell more details about G hat later?
More details about G hat. I'm not sure if I'm going to tell the details you want to be told, but we'll see. Okay.
The integral of G naught came inside the trace?
Let's see. Okay, so what we do here is we take this expression here and plug it in here, and then we take the integral over G naught of f of G naught inside the trace to get and define this object.
Can you motivate why such a formula should exist?
Well, yeah, so I mean, the space of function, I'm not sure this is going to be a good motivation, but the space of functions on the group is a representation. It's a representation of the group. It has both a left and a right action, and therefore you can try to decompose it into irreducible representations. If you have a sufficiently nice space of functions, maybe it's not surprising. Maybe it is. Maybe it isn't surprising that it has a decomposition into irreducible representations. And that's just what this formula is saying. So the space of functions on the group is called the regular representation, and the Plancherel formula gives the decomposition of the regular representation into irreducibles.
By function on the group, you mean that have a nice, if I feed the product of elements into the function, it spits out?
No, just any function on the group. It doesn't have to have any nice invariance properties, although we will shortly be interested in functions that do have nice invariance properties. But for this formula, so in this formula, f is any function on the group, literally any function, satisfying sufficient niceness conditions that I'll talk about in a little bit.
And this only applies for unitary irreps, or
Yeah, good. So I'm not precisely sure what the most general space of groups is for which a Plancherel formula has been proven, but there's some nice space of groups. I don't know. They're reductive Lie groups, something. And for those groups, yes, the only things appearing in the Plancherel measure are unitary representations.
Sorry, can you speak up?
What?
In the first place, you're decomposing regular representation, which is a unitary representation. So it's natural that in its decomposition we get unitary representation.
Okay, good. Did everyone hear that? Okay, so the statement is that the regular representation is itself a unitary representation. So it makes sense that it decomposes into unitaries. Thank you.
Does this apply to supergroup?
For that, you'll have to wait for the later lectures by Wikipedia, who's a new member of the Bootstrap collaboration. Yeah, I have no idea. Yeah, I mean, all of the super applications of these sorts of things that I've seen in physics used by by using some kind of bosonic Plancherel theorem underneath and dealing with the fermions on top. And of course, that can be a little cumbersome, but I think it could always be done in principle. Okay, good. So example 1 is just Fourier analysis. So that's the case when G is R, the group of translations. So the unitary irreps are, so let's see, this is translations. The unitary irreps are one-dimensional, and they're labeled by a momentum k, a real momentum k. So I'll take as the parameter on this group x, and so x in R. And the representation map is just given by, so I'm not going to write k of x because that's really terrible. So I'll write pi sub k for the one-dimensional irrep with momentum k. So the representation map is that if you do a translation by x, then in this irrep, you multiply by a phase e to the I kx. Okay, so what is this thing that I called the Fourier transform, f of pi sub k, which we'll also write as just f hat of k. So this is equal to an integral over the group, which is an integral dx from minus infinity to infinity of f of x times the representation map of x inverse, which is e to the I kx inverse. And these Fourier coefficients are matrices in the irrep. But here the irreps are one-dimensional, so the matrices are just numbers. So this is just a number. And of course, this is just the Fourier transform of the function f of x. And the Plancherel measure is dk over 2 pi. So we get a statement that f of x is equal to the integral from minus infinity to infinity, dk over 2 pi, f hat of k, e to the I kx. So just to belabor the point, not all representations of the group appear in the Plancherel measure. So we're only getting real momentum, and we might be interested, for example, in studying some function that has an expansion in growing or dying exponentials, namely complex momentum. And you could ask, well, what can we do with such functions? And one example is just the Fourier transform of 1 over cosh. So the Fourier transform of this turns out to be equal to 1 over cosh again. So that's not actually that important, although it's kind of a neat fact. Not important for us. And so we get an expression that says that 1 over cosh x is equal to an integral dk over 2 pi, pi over cosh k pi over 2, e to the I kx. So 1 over cosh has a nice expansion in dying exponentials at large positive x. And the way that comes about from this point of view is that when x is large and positive, we can take the integral over the k-plane, which is over some real values of k. When x is large and positive, this quantity dies in the upper half k-plane. So we can deform the contour into the upper half k-plane, and what we encounter are poles coming from the Fourier transform. So there are poles in the upper half k-plane. We can take the contour over the real values of k, and we can deform it like this and pick up the contributions of the poles. And that gives us some kind of sum over dying exponentials. So we get 2 e to the minus x. That's coming from the pole at k equals I, minus 2 e to the minus 3x plus dot, dot, dot. And this might look kind of silly, but this is the same sort of thing that will happen shortly in the conformal block decomposition when we write that using harmonic analysis. Okay, so the fact that the physically interesting things don't appear in the Plancherel measure shouldn't scare you too much. Okay, suppose you're interested for some reason in only in dying and growing exponentials. That's okay. You just have to do some contour deformation to see them. Okay, so good. So now let's do a slightly more complicated example that gets a little bit closer to the case of interest. So this more complicated example is going to throw in this case where the functions on the group that we're interested in have some nice invariance property. Okay, so we're going to consider a function on the unit 2 sphere. And we'll think of S2 as a quotient of its isometry group modulo SO2. So SO3 mod SO2. And more precisely, there's a quotient map from SO3 to S2, and that's given by taking G in SO3 and mapping it to the image of some fixed unit vector E. So this is a map from SO3 to the 2 sphere. And this map is invariant under right multiplication by SO2. Okay, so if I take G and replace it with G times H, where H is in SO2, then on the right-hand side, I get GHE. And specifically, we'll be interested in the SO2 that fixes this unit vector. So this is just G times E. That's because H fixes E. Okay? So good. So we have a function on S2. We can think of S2 as a quotient. And so that means we can lift our function on the sphere to a function on the group. So we just define f of g to be f of g times e. And I apologize for abusing notation. I'm going to use the same letter f for the function on the group as for the function on the sphere. So, so we haven't done anything that interesting yet. We've just taken this function on the sphere and lifted it to the group. But the fact that it came from a function on the sphere means that it has some invariance property. So it's invariant under right multiplication by SO2. So f of g h is equal to f of g for h in SO2 just by construction. So what we'd like to do is apply the Plancherel theorem to this function f and use this invariance information to simplify what we get a little bit. Okay, so the Plancherel measure for SO3. So first of all, the unitary irreducible representations of SO3 are our favorite spin-L representations that we all learned. They're the first representations that are not one-dimensional that any of us ever learn about. I think. Tell me if not. Some of you may just live and breathe conformal primaries. Okay, so this is the Plancherel measure on SO3. It's just a sum over those familiar unitary irreducible representations. Okay, so the Plancherel theorem tells us that f of g is equal to a sum from L equals 0 to infinity, 2L plus 1 over the volume of SO3. Now, what we're going to do here is plug in that final formula on the board up there as a sum over matrix elements in these different representations. Now, we know a basis for the spin-L representations. They're labeled by little m that runs from minus L to L. So A and B are going to instead write them as m and m prime. They run from minus L to L. And then we have a matrix element in the spin L representation times a Fourier coefficient and so now, now let's use invariance. So this expression is true for any function on the group, but we're not just interested in any function. We're interested in a function that is invariant under right multiplication by SO2. And what that means is that M prime appearing here must be 0. M prime must be 0 because M prime equals 0 is the state that is invariant under SO2. Okay, so we're going to take these M's here to be the basis elements with respect to the SO2, the interesting SO2, the one that fixes this unit vector. So only the M equals 0 state is invariant under SO2, and so only matrix elements of that form can appear in this expansion. So this double sum turns into just a single, well, this double sum over M turns into a single sum. And it looks like this. Okay. Yes? Yeah, it's right multiplication. So only if you replace G with GH do you have to be invariant. If you replace G with HG, then anything goes. So I'll just pi L of GH is pi L of G, pi L of H. And then this thing leaves M equals 0 invariant. So that's what we're doing. Okay, so this is actually something that we all know and love. The reason is that these matrix elements are precisely spherical harmonics. Okay, so here we've written them as a function on the group, but we know that they're actually just functions on the sphere because the group is, because the sphere is SO3 mod SO2. If we replace G with GH, then this thing is invariant, so it actually descends to a function on the sphere. So it's a function on the sphere labeled by L and M, it has to transform in the spin L representation under left multiplication by G, so that basically fixes it to be this spherical harmonic. So yeah, if M prime is not 0, these give generalizations of spherical harmonics that sometimes appear in different cases. Vector harmonics, spinor harmonics, stuff like that. So that would be the case, if you like fancy words, that would be the case where you're trying to describe a certain section of a line bundle over the sphere instead of a function on the sphere. Okay, so this is just an expansion in spherical harmonics. And this coefficient function, we can use the Plancherel formula for it. This is the integral over the group of f of g times y star Lm of ge. So it's the integral, and this, of course, descends to an integral on the sphere. Sorry for this notation getting a little bit crunched. So we can write this as volume of SO3 divided by, well, let me not, okay, write it over here. Okay, so we can write this function, this integral on the group as an integral over the sphere if we take care with. So what we're going to do here is this is an integral over the group, but everything appearing here is invariant under g goes to gh. So we're going to do the integral over that fiber. We're going to do the integral over the h direction. And I'm going to write the integral over the fiber, the integral over SO2, like this. Okay? Then we just end up with an integral over S2, dn, f of n, y star lm of n. And so these are up to this funny factor. So you can see that the volume of SO3 here is going to cancel with the volume of SO3 here. And that I think I'll elevate to a general principle. Whenever you have the volume of a group in the subject, it's going to cancel eventually. So we're left with sum of 2L plus 1 over 4 pi times the integral of the function against the spherical harmonic times the spherical harmonic. And that may be a familiar formula to many of you. Okay. Okay, good. So we don't have time to do much more, but I want to set up the thing that comes next. What we're going to do next time is we're going to do harmonic analysis for the Euclidean conformal group, SOD plus 1, comma 1. We're going to consider a correlation function and focus on the behavior of this correlation function as a function of these two positions. So that's why I'm writing these differently. We're not really going to care about what's going on with these other guys. We just have these two operators, and we're going to do something interesting to them. What we're going to do is take this correlation function and lift it to a function on the group by writing these guys as some group element acting on phi at 0 times phi at infinity. So using the conformal group, we can move the 2 points 0 at infinity to any 2 points we like. And so writing this in this way, this correlation function becomes a function on the group. We then apply the Plancherel theorem to this function on the group, and we're going to end up with what's called the conformal partial wave decomposition of this correlator. Okay? Yes?
Why is that hat only labeled by L? I would expect it to be labeled if f of g is general functions on S2, then only both L and M.
Good. So f hat is a matrix. So the m's are hidden in the element. They're the elements of the matrix. So most generally, f hat is a square matrix whose rows and columns are labeled by m and m prime. The case you're familiar with is where one of those rows is always the 0 row. It's the dimension of the representation. So later we're going to have infinite dimensional representations, and the sum over m is going to become an integral. Joao?
Is there a general formula for this Plancherel measure?
Yeah, good. I actually don't know. I'm sure that's known, but I don't know. I think there are general formulas for large classes of groups. There's certainly a general formula for the. There's a general formula for all Euclidean conformal groups. I'm not sure there's a general formula for all Lorentzian conformal groups yet, for example. What's that? There is, but it's hard to understand. Okay, but it's not known to Wikipedia, I believe.
In general, the unitary dual is not known, the G hat.
The G hat? What does in general mean?
I mean,
just
only specific groups that you just named
Uh-huh.
can compute it
Uh-huh.
to know what unitary representations show up.
But we don't need the unitary dual. We need only those representations in which Plancherel measure has support, which is central representations and which are known for large classes of groups.
Other questions?
like this should I be able to write all the time, like process of groups or groups themselves to be able to use this method, or does it extend beyond that?
I'm not sure I understand the question. So what kind of case would you want it to extend to?
Maybe I need to think about it.
Okay. Good. So let's stop there. Thanks. Okay, so this afternoon is free time for problem solving. Like I said before, we do not have the 4th floor of Downs Lawrenson available for everyone. You can go up there, but there's a lot of stuff because they're setting up for the reception at 6 o'clock. So I recommend using this room if you want to work on problem sets, or there are some classrooms on the 1st floor and in the basement of Downs Lawrenson that you can go to, or you can go outside if you want to work in the sunshine. What's that? Oh yeah, the problem sets are on the website at the bottom of the school page.